have done two different examples, or two different example videos of energy conservation, but I'm going to do a third. So in the first example, I gave you just gravity near the surface of the Earth as a source of potential energy. For the second example, we combined that with a spring. For this example, we are going to look at what we've been calling big gravity as a source. So if I have a planet like this, and I have an object, let's say a very squarish shaped rocket, and maybe I want to launch that off the surface of the planet. So I'm going to give this thing some numbers. We can make this thing the Earth. We can give this a mass of 6 times 10 to the 24th kilograms, a radius of 6.4 times 10 to the 6th meters. Now it's Earth. Guess that doesn't define it as Earth, but it's characteristic of. I want to take this rocket and give it a mass of, we'll go 1,000 kilograms. This thing's pretty big. And I would like to take that rocket and shoot it out into space. I would like to shoot it so high, in fact, that it doesn't come back. Now this isn't really the way rockets work, right? We don't just take a rocket at the surface of the Earth, put it on like a spring or something, or give it a kick and say, hey, good luck. Instead, we have this continuous burning of fuel, and that looks a little bit different. So bear with me on this. It's a little bit of a different idea. Although there was a project some time ago called Spin Launch that the idea was that they were going to just take these blocks and launch them into space. They weren't going to be propelled along the way. You were just going to effectively throw this thing up into space, and that's the idea here. I'll provide a link for that because I thought it was interesting. So what are we doing? We are looking at potential energy and kinetic energy. In this case, my initial point is going to be at the surface of the Earth, and my final point is going to be out in space. So I will have potential energy, kinetic energy, and total. And there is my table. My initial kinetic energy the question that I would like to ask is, how fast do I need to launch this thing to get it into space to not come back? So my initial kinetic energy is actually going to be an unknown. Half m v initial squared. My initial potential energy, that's going to be a negative g, mass of the planet, mass of my block, over just the radius of the planet, which I will call a capital R. My final potential energy and final kinetic energy, here's where things get a little bit weird. So my final kinetic energy is going to be 0, and I imagine you guessed that already. If this thing is going to not come back, and I'm looking for the minimum launch speed, then I would like this to get out to a certain height and just have a speed of 0. I don't want any wasted energy in this process. So a final kinetic energy of 0, that's fine. A final potential energy. When I talked about the potential energy on a large scale, what I said was that as we get farther and farther from a planet, we are going to get this kind of potential energy curve that just kind of levels off. If we can get to a point of potential energy 0, which we can't, that'll be infinitely far away. But if we could get to a point of 0 potential energy, then this thing won't come back. That's the point that I'm looking for. It is fictitious. Realistically, what we're going to do is get to a point where our total energy is 0, where we know we are going to be far enough away and moving at the right speed to get a total result of 0. but it's the same effect as stationary with no potential energy. So our final total energy is 0. Our initial total energy, negative g m over r, plus half m v initial squared. And that's it. From here on, it's the same problem that I've already solved a couple times. I'm going to set my initial energy equal to my final energy and start solving. Half m v initial squared. I'm going to take this whole term over here and move it to the other side of the equation. So it equals g mass of the planet, mass of the object over r. I can cancel the mass of my object and solve for v initial. V initial is going to be 2gm over r, all under a square root. And now I can start plugging in. 2 times g is that universal gravitational constant. Mass of the planet, I am looking at the Earth, so I've got that 6 times 10 to the 24th. The radius, 6.4 times 10 to the 6th meters. And now, because of this project, this spin launch project, I actually have a real life problem with this. Even though you will find that these numbers are not particularly realistic. This spin launch was never going to work for launching things out of orbit, just for launching them into low Earth orbit. But here we go, plugging in those numbers, I get about 11,000 meters per second. It's actually a little bit faster. In case you want a conversion, 11,000 meters per second works out to be almost 25,000 miles an hour. We've got to launch this thing fast if we want it to get completely away from the planet and not come back. Now there is something that I should mention here. We didn't talk about the direction of this velocity at all, we just talked about a speed. If I launch this thing at 11,000 meters per second, it's not coming back. If I launch it at 11,000 meters per second in this direction, it's still not coming back. Really, I can launch this in any direction at all that isn't down because I'm going to run into the ground. I can launch this in any direction at all at that speed, and this thing is not coming back in an idealized situation. So then what's the reason that with rocketry we launch things straight up? Well, we are simplifying this system. In this system, in this problem, we are ignoring things like air resistance. If we didn't have air resistance, so if the Earth didn't have an atmosphere, well, one, it would be really difficult to launch things because we wouldn't be around to breathe. But if we could somehow figure that part out, it would actually be easier to launch things. The air resistance plays a major, major role. And the faster we can get into a thinner atmosphere, the less air resistance we have to deal with. So launching something straight up is actually really advantageous because we get out of the thicker air faster. We have less to contend with. But in the world of these kind of intro-ish physics questions where we are looking at a planet without thinking about air resistance, we're looking at a planet where everyone holds their breath, literally, through every launch. It doesn't matter what direction we're launching. We're going to make it out into space.